Let's see my notes here. Okay, I do have an office hour today. It's at 11 o'clock. And I'll do my best to remember it. Okay. Okay, so we had some questions about those limits as x goes to infinity. Let me work a couple of problems for you. I'm not going to work your homework problems, but okay, so let's share content. Yeah, what Mr. Levy said is true. Broadcast to Zoom? What? Okay. Yeah. Oh, okay. I don't know what that was. Good old internet. Full of surprises. Okay, this is differentiation rules, which are not to be used on the homework you submit today. Okay, but let's see, I told you that I would do a couple of those limits as x goes to infinity. Okay, so let's how about I do 3 problems? And let's see, let's have to do that, and we do square. I'll make this one go to minus infinity because it's similar. Okay. So kind of 3 different cases. Okay. So if you want to take the limit as x goes to infinity of 1 over x plus 2, well, what's happening here? You're taking larger and larger numbers. Yeah, you want to pay attention to what x is going to. Okay, x is not going to a number here. It's going to infinity, which is another way of saying that x is getting larger and larger and larger without bound. Okay. So you're putting in large numbers here. X is large. If x is a large number, 1 over x, well, x plus 2 is larger, but 1 over x plus 2 is close to 0. This limit is just 0. Okay, and in fact, the limit as this is equal to 0. Okay. I think I mentioned that when I was talking about these before. And well, okay, we have a little bit more complicated situation there. It's x plus 2, but it's the same idea. And it, yeah, here also, if well, n greater than 0, if I'm putting a positive number in, large positive number in for x, and I raise it to the nth power, that's a large positive number. Oh, wait a minute. Wait a minute. I think I need n greater than 1, greater than or equal to 1. Yeah, that helps. Then this is always true. But just think about it. if x is a large number, x plus 2 is even larger. And then I take 1 over the large number x plus 2. That's a number close to 0. So, and that's the larger x is, the closer 1 over x plus 2 is to 0. So the limit in a case like this is 0. If I take, okay, this is another example. So I've got a second-degree polynomial over a second-degree polynomial. And this is really, okay, a form of a limit. The limit as, oops. The limit as x approaches infinity of just the numerator. Okay, well, that's infinity. And the limit as x goes to infinity of the denominator is also infinity. That is, if I put in a large number into x squared plus x plus 1, well, if x is large, x squared plus x plus 1 is even larger. And the same thing's true for x squared plus 2. So this is another form of a limit. Okay, this is the infinity over infinity form. Again, just like 0 over 0, infinity over infinity is not a number. In fact, infinity itself is not a number, which is why you have to be real careful with it. Okay, so what can you do? Well, we've been looking a lot at what happens when you have the 0 over 0 form, that when you're using the limit definition for derivatives, you're pretty much always dealing with this. This is another, what you call, indeterminate form. And just like we did with our other limits, what I'm going to do is to change the form of the problem, but not change the problem. I'm going to change it algebraically. I'm going to, okay, since that's a second-degree polynomial in the numerator and a second-degree polynomial in the denominator, I'm going to multiply the top and the bottom by 1 over x squared. Which means, well, 1 over x squared divided by 1 over x squared is equal to 1. I am not changing the problem. And that, but this helps me because, okay, if I multiply that 1 over x squared through, x squared times 1 over x squared is 1. 2x times 1 over x squared is 2 over x. And 1 times 1 over x squared is 1 over x squared. And then in the bottom, x squared times 1 over x squared is 1. 2 times 1 over x squared is 2 over x squared. And now I can see what's happening, okay? As x goes to infinity, two over x goes to 0. And so does 1 over x squared and 2 over x squared. So this goes to 0, this goes to 0, this goes to 0. And I can just direct substitute then. Okay, well, I'm not putting infinity. Okay, it's not direct substitution. You can't put in infinity for x. Okay, but the limit is, I can evaluate 1 plus 0 plus 0 over 1 plus 0 is 1. In fact, in general, if you have a nth degree polynomial divided by an nth degree polynomial, you're going to get a limit. That's a number. Sort of what happened here is I had a 0 degree polynomial, constant, divided by a first degree polynomial, when the degree of the denominator is bigger than a degree of the numerator, and you're taking x goes to infinity, you're going to get 0 because the numbers on the top are not growing as fast as the numbers on the bottom. And here we have the degree of the numerator is.
I had a quick question for that.
Sure.
How did you decide to multiply it by 1 over x squared?
Oh, because the highest degree is 2. Let me go, okay, let me go back and see if there are people I need to admit.
So to find, oh, I'll wait until everyone gets in before I finish.
No? Okay. That's amazing. All right, so back to the screen. And I must do it correctly.
So as I was making sure I understood, the number you multiply both the top and bottom by is the highest shared
Yeah.
Your number over over 1 or under 1, I mean.
Oh, okay, wait a minute. Let me go back.
I meant like you give it a fraction form with 1 over the highest shared exponent, correct?
Well, yeah, but okay. So if the degree of the top is equal to the degree of the bottom, you're going to multiply 1 over x to that degree.
Okay, that's what I was making sure I understood.
Okay, but here, let's see, here you've got, this is going to minus infinity, but x to the 4th over x cubed plus 1. Now the degree of the numerator is larger than the degree of the denominator. So these numbers, okay, just thinking about it, these are getting large faster than these are getting large. And in this one, okay, but the same kind of thing would work. Let's see. Well, this one's not going to have a limit. Okay, but let's see I'm going to try the same sort of thing here. Do I want to? Okay, let's try this. There's my problem again. But the degree of the numerator is 4. So, okay, I'm going to try multiplying by 1 over x to the 4th divided by 1 over x to the 4th. And let's see what that gives me. That's going to be the limit as x goes to minus infinity of 1 over, okay, well, x cubed times 1 over x to the 4th is 1 over x. This may not have been the best. Now, okay, I want to go back and change that. Okay. I guess you can see from this too. Okay. But, okay, suppose, well, if I'd done, you have a lot of leeway here. As long as you don't change the problem, you can think about it in different ways. Let's see if this would be better. Okay, I'm going to try 1 over x cubed. Maybe that's going to be more straightforward. That would be, okay, so I'm still multiplying by 1. So I'm not changing the problem. Okay, you're not allowed to change the problem. You are allowed to write it in different ways. If I try the 1 over x cubed over 1 over x cubed, multiplying that by the original expression, and let's see, that's going to give me x over 1 plus 1 over x cubed. Okay, well, either one works actually, but okay, so what's happening here? Well, if x is a large negative number, like minus a billion or minus a trillion or the size of the US debt, something like that. 1 over x cubed is very close to 0. Okay, so that's going to 0. But what's happening? Yeah, so the denominator is going to 1. All of that is x large negative 1 plus 1 over x cubed is close to 1. But what's happened in the numerator? The denominator numbers are getting close to 1. The numerator numbers are getting larger and larger in the negative direction. And they're not bounded. This limit's going to be, okay, let's see, minus infinity, because they're going to be negative numbers. Okay, and just looking at this, I have a 4th degree polynomial divided by a 3rd degree polynomial. The top numbers, as you go to plus infinity or minus infinity, are going to be getting large without bound in either the positive or negative direction. These numbers are getting larger faster than these numbers are. And the limit's not going to exist. Oh, okay. Let's see. Any questions? We're going to say a lot more about these kinds of limits later. And in fact, well, today in my 2nd semester calculus, we're going to talk about something called L'Hopital's rule. That's a really slick tool for dealing with limit problems, but we don't need to see that yet in your class because it would be confusing at this moment. Let me do one more example for you. Suppose you have one with a square root in it. Like number 14. Only I'm not going to do number 14. Okay, so I need to make one up. X squared over the square root of x to the 4th plus 9. Suppose we have that. For this one, okay, that radical, I cannot simplify that denominator, okay? Because the square root of a plus b is not equal to the square root of a plus the square root of b. That's so wrong. Cannot simplify the denominator. What I can do, okay, write it in a different form. I can write x squared as the square root of x to the 4th. And now, well, the square root of a over the square root of b is the square root of a over b. That's from algebra. So this is the limit as x goes to infinity of the square root of x to the 4th over x to the 4th plus 9. And now I can use the limit laws. If this limit exists, and if it doesn't, I'll find that out too. I can bring the square root out. Of the limit. Okay. So, well, it's a limit law. I don't remember what number. Okay. Need all of them. Okay. But that's x to the 4th over x to the 4th plus 9. And if I take the limit as x goes to infinity of just what's under the radical there, that's equal to the limit as x goes to infinity. And well, it's x to the 4th and x to the 4th. So I'm going to multiply top and bottom by 1 over x to the 4th. And that's equal to the limit as x approaches infinity of 1 over 1 plus 9 over x to the fourth. And now it's easy to see what's going on. 9 over x to the fourth, for x large, that's going to be really close to 0. So the limit's going to be 1 over 1 plus 0, which is 1. Okay, that gives you some examples. And in fact, these are very much like your homework. Okay, any questions?
I have a question.
Okay.
So is there ever going to be a case where the limit doesn't equal 1, 0, or infinity?
Oh, yeah.
Okay.
Okay, so, well, what if I had, okay. And we're mostly just talking about polynomials or things you can convert into polynomials. That one's going to have a limit of 3. So it can be any number. Okay. But if you've got polynomial over polynomial, it is completely determined by, okay, if the degree of the numerator is equal to the degree of the denominator, and you're going to either plus or minus infinity, you're going to get a limit. If the degree of the numerator is less than the degree of the denominator, then you're going to get a limit of 0, because the denominator is getting big a lot faster than the numerator is. On the other hand, if the degree of the numerator is greater than the degree of the denominator, then the numerator is getting big faster than the denominator, and you're going to get plus infinity or minus infinity. So yeah, it's either no limit. Okay, this is polynomial over polynomial, or one you can convert to polynomial over polynomial. You either get no limit, and the no limit is of the form plus infinity or minus infinity. If degree of the numerator is equal to the degree of the denominator, you're going to get a number, get a limit that's a number, okay, that's not 0, actually. And if the degree of the numerator is less than the degree of the denominator, the limit's going to be 0. But okay, I probably didn't say enough about these before. Okay, but I said considerably more today. And we'll be coming back to this kind of thing. So we're going to learn, yeah, for the most part right now, we're just talking about rational functions or polynomials over polynomials. And even though this last one, that's not a rational function. But I use the limit laws to convert it to, well, to get the limit to be limit of a rational function. In fact, I didn't finish that because that was the inside. So this limit is the square root of 1, okay? Because the inside goes to 1, and then I take the square root of whatever the inside limit is. Okay. Let's go back to, okay, so this is homework stuff. Let's go back to our differentiation rules, okay? And again, I do not want you using these on the homework that's due today, nor do I want you using them on the exam we're going to have next week. For the homework and the exam this week and next week, I want you to use the definition of derivative, which means compute one of those limits. The differentiation rules are shortcuts because if you've done your homework, computing that limit, well, every single time, that's a little tedious. And in fact, for some function, it'd be really hard. So if you have these rules, you can break up your problems and get an easier way to do it. But the reason that these rules hold is because we actually use the definition to prove that they hold. Okay, we proved this one, we proved that one, we proved that one, we proved that one, we proved that one, and we proved that one. And I'm not going to prove any more. Maybe much to your relief. I don't know. Well, I want to emphasize the reason these rules hold is because you use the definition to show that they hold. Okay, number 6 has a name. It's called the product rule. And we actually proved it. Number 7 has a name. It's called the quotient rule. And actually, I'm not going to prove it. The proof is not, it's very similar to the proof of number 6. So it's not difficult. And I don't know if we'll get to number 8 today, but number 8 is called the chain rule. Okay, and it tells you how to deal with derivatives of composite functions. Okay, so we have the product rule and the quotient rule, and we have all the rules that came before that. And this is really going to make our lives easier as far as computing derivatives. Here's an example. Differentiate the function f of t is the square root of t times 1 minus t. Well, actually, I could do this one 2 different ways. I could use the product rule, or I could multiply out and then use some other rules. But okay, let's do it both ways. In fact, let's see. Let me, since I've got all this stuff in the way, let's just come down and go after it. Okay, so example. Okay, so make sure I have the same problem as before. I guess. So first way, I'm going to use the product rule. So the derivative of f of t would be the derivative of the square root of t times 1 minus t plus the square root of t times the derivative of 1 minus t. Remember that d means derivative. Okay. And helps to write square root of t as t to the 1/2. Make absolutely sure that I know where my derivative part ends. Okay, so now let's take some derivatives. Well, using the power rule, that the derivative of x to the n is n x to the n minus 1. The derivative of t to the 1/2 would be 1/2 t to the minus 1/2. Okay, because 1/2 minus 1 is minus 1/2. Oops. Times 1 minus t. And then t to the 1/2. The derivative of 1 minus t is, well, the derivative of 1 is 0, because that's a constant. The derivative of minus t is minus 1. And it's t to the first power, so the derivative is 1 times t to the 0 power. Think of it that way. So we wind up with, oh, no, 1/2 t to the minus 1/2. Get some light out. Minus t to the 1/2. And so this is fine. That is a derivative. I could also multiply out times 1 minus 1/2. T to the 1 to the minus 1/2 times t. Well, that's t to the first. So we have 1/2 t to the minus 1/2 minus, okay, and then t to the minus 1/2 times t to the 1. Here we use the rule a to the r times a to the s is a to the r plus s. 1/2 minus 1/2 plus 1 is plus 1/2. Okay, so that would give me, and I could combine those two t to the 1/2. Minus 3/2 t to the 1/2. Okay, so any one of these is fine. And perhaps I should check my work here. I think that's okay. Any questions? Okay, well, what if we multiplied out first and then took the derivative, and then we wouldn't have to use the quotient rule? We should get the same answer, okay, because there's only one derivative. All right, so let's see. F of t is the square root of t times 1 minus t. Well, that is equal to the square root of t minus t times the square root of t. And if I change that to the exponential notation, that's t to the 1/2 minus t to the first times t to the 1/2, which is t to the 1/2 minus t to the 3/2. Okay. So I've written my function in a different way. I have not changed it. And if I write f of t like that, then I can just use the power rule on both pieces. Excuse me, got congestion this morning. 1/2 t to the minus 1/2. Okay, use some power rule, and then power rule there too. Minus 3/2 t to the 3/2 minus 1 would be plus 1/2. And okay, notice we got the same thing here as we did above. So you could have done it in two ways, depending on how you wrote your function. Let's do a problem. Any questions before I go further? Okay, let's do a quotient rule problem. Let's take the derivative. Oops. Let's see. X squared plus 1 over x squared plus 2. Now, I cannot simplify that function. Okay. The fact that I've got a sum that divided by sum and then the quotient of those, I cannot, well, I could write it as a sum of two functions, but I don't think that would make it easier. I could do this legally. But I've got a sum in the denominator, and I can't break that denominator up in some way. Okay? Can't cancel out the x squareds. That's not legal because x squared is not a factor on the top and x squared is not a factor on the bottom. Before you can cancel, you have to have factors, products, not sums. Okay, but I can use the quotient rule. I have a function of the form f of x over g of x, and the derivative of that, according to the quotient rule, derivative of the top times the bottom minus the bottom times the derivative of the top over the bottom squared. You're going to need to memorize these rules, but not this week. Okay. So let's just write it out. My top function is x squared plus 1. And my bottom function is x squared plus 2. So I want the derivative of x squared plus 1 times g unchanged. Oops, why don't I go ahead and put the function in? Times g, which is just x squared plus 2, minus f unchanged, times the derivative of g, all over x squared plus 2 squared. Okay, because that's g of x squared. Well, the derivative of x squared plus 1, I hope maybe you're kind of able to do this in your head almost at this point. I've got, well, the sum of two things, the derivative, so it's the sum of the derivatives. And the derivative of x squared is 2x. The derivative of a constant, 0. Okay. The derivative of x squared plus 2, that's your denominator function, is equal to the derivative of x squared plus the derivative of 2. Put parentheses, yes. And that's equal to 2x plus 0. So they're both derivatives are 2x. So we've got 2x times x squared plus 2 minus x squared plus 1 times 2x all over x squared plus 2 squared. Now that is the derivative of x squared plus 1 over x squared plus 2. That's it. You can also, okay, that's a little messy looking. We can use some algebra to simplify it. Well, some. That denominator is not going to simplify, I don't think. Unless something amazing happens in the numerator, which I doubt it will, but let's just see what we could do. Well, in the numerator, both terms have 2x in them, so I could factor that out. And then I'll have x squared plus 2 left from that term, and from that term, I'll have minus x squared plus 1 left, okay, because remember I have that minus there I can't forget about, okay. And that's over x squared plus 2 all squared. So the x squareds add out. And then I've got 2 minus 1, so that's just 1. Okay, so that's looks a lot nicer than that did. Okay. But let me emphasize, this is the derivative. This is the derivative. And this is the derivative. If you want to use the derivative, and okay, we're going to want to use the derivative because why are we learning about it if we're not going to use it? We're going to want to use derivatives to do a lot of things. It's better to have it written in this form if you want to use it. Any questions? Are y'all still there?
Yes.
Oh, good. Thank you. Okay. All right. Let's see. It's 8:42. Got time for another example. How about this? Okay. Well, we haven't mentioned any of the trig functions yet, and I'm going to spend an entire class talking about those. But let me just tell you now, the derivative of the sine of x is equal to the cosine of x. And okay, why do I know that? Well, what you have to do is to go back to the definition. Let's see, maybe I use the H definition. Oops. Got 0 in the brain after this morning. There. Its limit as h goes to 0 of the sine of x plus h minus the sine of x all over h. Yeah, go back to this definition, and then you got to work on this. Okay, you got to look at what happens. Well, you can use there's a formula for the sine of a plus b. We can use that, and then we can talk about some other things, and it gets a little complicated. But you work on this, and you do a lot of work in between, and this limit turns out to be the cosine of x. But there are a lot of steps in between. Okay, so let's just use this, and I think we can make an interesting product. Okay, so example. Find the derivative of x squared plus 1 times the sine of x. And that's a product of two functions, the sine function and a polynomial function. So we can use the product rule. And the derivative then of x squared plus 1 times the sine of x is equal to the derivative of x squared plus 1 times the sine of x plus the sine of x. No. Okay, plus x squared plus 1 times the derivative of the sine of x. Okay, and the derivative of x squared plus 1, well, the derivative of x squared is 2x, the derivative of 1 is 0. So that's just 2x times the sine of x plus x squared plus 1. Derivative of the sine of x is the cosine of x. And that's the derivative, and I don't see how you can write that in a simpler form. Okay, that's just it. Let me do one more example, and then maybe we'll call it a day. Yeah, so after today, you know how to use everything up through the quotient rule. We'll talk about the chain rule on Monday and maybe get into the derivatives of the trig functions. How about we do this example? Oh, my ladies are here. Just a second. Come in. Good morning. I am teaching my class. Okay, let's find the derivative of, well, how about we just make that problem into a quotient of two functions. So x squared plus 1 divided by the sine of x. Now we have to use the quotient rule. So the derivative of x squared plus 1 over the sine of x is the derivative, so f prime times g, derivative of x squared plus 1 times the bottom function unchanged, minus x squared plus 1 times the derivative of the bottom function over the bottom function squared. And that's equal to 2x, okay, derivative of x squared plus 1 is just 2x plus 0 times the sine of x minus x squared plus 1 times the cosine of x. And then over this, okay, the sine of x all squared, which is also customarily written as the sine to the power 2 like that, yeah. Yeah, so sine of x to the n, you're right. People use that notation. But the sine of x to the n is not the same thing as the sine of x to the n. We're going to talk about this kind of thing on Monday, okay? Both this function and that function are composite functions. In the left-hand function, the sine of x is on the inside, and then first you take x, you take the sine of x, you get a number, and then you raise that to the nth power. In the second function, the one on the right, you take your number x, you raise it to the nth power, and then you take the sine of it. So the inside and outside change. But okay, we will talk about that Monday. Any questions? Okay. If no questions, you can go. Okay. End of class. Have a good weekend, everybody.
You too.
You too.